In this video, we're going to talk about conductors. So we talked about conductors in the electric field chapter, and now we just want to talk about how conductors fit into the picture with energy and with potential. So what I'm going to do is go over what we already know about conductors, and then I'm basically adding one additional fact to that list of facts about conductors. So remember that conductors, you're thinking about metals primarily, and what makes metals a conductor is that they have these freely moving electrons. They have these electrons that are not attached to specific atoms, and so they can flow, they can move throughout the metal and do whatever they need to do. They're free to move. Okay. The other thing before I get into the list of facts is to remind you that this list of facts applies when the conductor is in electrostatic equilibrium, as you see here. And what that means is this is like after everything has settled down and things have stopped moving and those free electrons have stopped doing what they need to do. This is after all that has finished and we're in a static situation. Then and only then the facts that we're going to go over can be counted on to be true. Okay, so let's see. What we know is that free electrons will move to cancel any external electric field. They will do whatever they have to do so that any external electric field that exists will be zeroed out on the inside. And in fact, that's fact number 2. The electric field is zero inside the conductor, inside the outer boundary. So that's actually like the interior, the inside of the metal, but it could also be inside any cavity, like any hole that's inside the metal. So it's anything within the outer boundary of the conductor. The free electrons will move. They'll do whatever they need to do so that electric fields get canceled out. Whether it's the electric field created by the conductor itself or whether it's the external electric field, as I have written here, whatever the situation is, there will be no electric field inside the conductor. Again, at least after things have settled down, electrostatic equilibrium, that is definitely true. Now, there can be and would be an electric field on the outside, and it will go right up to the boundary of the conductor. But then, of course, it stops, and inside the electric field will be zero. And the external electric field will be perpendicular to the surface. And in fact, we can connect the magnitude of the electric field to how much charge is on the outside. So just a picture that goes along with this. Here's the purple is some hunk of metal, some conductor, irregularly shaped. There will be no electric field on the inside. And what you see on these blue lines on the outside are the electric field on the outside. And whatever it is, however strong it is, it will hit the surface perpendicularly. So you see these lines are all going sort of straight out, perpendicular to the surface. Okay, now as these lines extend, I haven't drawn them further out because they can do whatever. Once they get a little bit away from the conductor, they can turn, they can it could be a uniform electric field all along the outside here, except right in the vicinity of the conductor, whatever. But right sort of approaching the conductor, they have to come straight in. I also haven't drawn the arrows. The arrows could be pointing away from the conductor or into the conductor, depending on how those free electrons have arranged themselves and whether there's sort of negative charge at that part of the surface of the conductor or positive charge at that point. Okay, so that would depend on the situation and on what else is going on, like whether these arrows are coming in or going out. Some of them might be going in, some of them might be going out. That's fine. Okay. Everything I've said up to this point is true whether or not the conductor itself is charged. Remember, the conductor could be totally neutral overall, but it has the ability to create locally positive and negative charge because these electrons can move. So like all the electrons could migrate to one side, creating more negative charge over there and leaving positive charge on the left side, and that is all true, but the overall thing would be charge of zero. Well, in some cases, conductors are charged. They do have a net charge that isn't zero. And the fourth fact that we learned, and again, this is all still review from a previous chapter, the fourth fact we learned is that any extra charge, whether it's positive or negative, that will all go to the edges. Okay, and it will help in canceling out the external electric field. Maybe fewer, maybe not as many of the free electrons have to move around if you have some extra charge to help out. Okay, but that extra charge will all go to the outside. It has to, because if it was on the inside, there would be some electric field in there, and we know that can't be the case. Okay, so now that's all great. That's well and good. Now, what can we say about V, the electric potential, with a conductor, with a charged conductor, or even if it's not charged? And the fact is that the electric potential is constant everywhere within the conductor. 1V, one number for the whole conductor, the edge, the surface, the inside, all that. Also any cavities on the inside, all of it is all at 1V. And the reason is, if we just remember a fact about the connection between E and V. E is the derivative of V, we learned. And we also know that E equals 0. So put those two things together. E is 0, and E is the derivative of V. So 0 is the derivative of V. In other words, the only way that can be true is if V is not changing, right? We're saying the rate of change of V, the derivative of V, is 0. V must not be changing. Hence, it's constant. So that's a real easy jump. If you just go from E equals 0, you immediately get a constant V, a constant potential. So what that means is the whole thing is just one number. So like we can say, like a hunk of metal, any conductor, any object that is made out of conducting material, it has one V value. We can say that this conductor is at 1,000 volts, and that's enough because the whole thing is at 1,000 volts. All right, so that's the new statement. The first four things we had already covered, and this fifth fact is the new thing. I'd like to just apply this to a simple situation, the simple situation being a sphere, so a metal sphere or a spherical conductor of some sort. And let's assume it has some charge to it. Let's assume it has some charge. And we'd like to talk about, all right, what is the potential? What does the potential look like based on this charged spherical conductor? All right, well, we know that from outside a sphere, right, this has been a fact that we've been using for a while now. From outside a sphere, the sphere looks like a point charge, right? It's as if all the charge is right in the center. If you're outside, it's the same effect, right? So we can use the formula for potential that we use for point charge. Ke times the total charge divided by R, where R is measured from the center. It's how far away you are. Okay, so let me draw a few, let me move this over. Let me draw a few equipotential lines. So I just drew, well, it's a line because it's a two-dimensional, but remember this is really a 3D situation. There's a sort of a spherical shell around the actual conductor, and let's say that is, I'm just making up numbers here, 400 volts. Let's say that, you plug in Ke, the charge, and you divide by the distance, and you get 400 volts right there. Okay? Positive 400 volts, so I'm assuming that this conductor has positive charge on it. Let's say that's 300 volts. And that'd be 200 volts. As you get further away, the voltage would go down, the potential would go down. Of course, remember, 0 is at infinity. Maybe 100 volts is way out here. Okay, maybe this inner ring that I just drew is 500 volts. And notice that these, even though I'm going by hundredths, these are not equally spaced because it's inversely proportional to r. So it's not like yeah, these equipotentials would not be equally spaced. Okay, and all this just, I'm just making up the numbers, but it would be something like this. That would be the potential field on the outside. Now what happens once you get to the sphere and then on the inside? Well, let's say that right at the surface, I won't draw the circle, but right at the surface, let's say that that's 650 volts. Well, right at the surface is 650 volts. What we just learned is that any conductor, the V is constant all throughout. So actually the whole thing would be 650 volts. So the voltage goes up, 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 up until you get to the sphere itself, and then it just stays constant, and there's just one number for the whole sphere. Inside, on the edges, everywhere in this sphere, 650 volts. Whether this is a hollow sphere or a solid sphere, doesn't matter. 650 volts throughout the interior out to the surface. So if the radius of the actual physical sphere is capital R, now remember little r is just like how far away you are to the point where you want to figure out your potential. All right, so but inside, let's say so r, so on the inside, the formula would be the same formula, except instead of putting in different little r's depending on how far away you are, you know, really close to the center, almost at the out to the outer edge, whatever, we actually just always use this one r. You use the overall radius of the sphere, and that's even for points on the inside. Doesn't matter. You don't use a little r, you use the actual radius of the sphere. So that's just one number all the time. Okay? And I'm assuming, like I said, I'm making up the numbers in this case. We'll do a more concrete example in just a second, but I'm assuming that that comes out to 650 volts. And like I said, charged conductors have one potential, one number, and you just say it. This conductor is at 650 volts, and it's the whole thing. Okay. Just to show you in one more way what I'm talking about here, if I graph the potential as a function of r, as a function from how far away I am from that middle point, and let's say here is capital R, so here's 0, so anywhere between here and here we're inside the sphere, and then after that we're outside the sphere. Okay, so we're following this formula on the outside, and you know, a number divided by r kind of falls away like this, dies out like this. But then once we get to the boundary of the sphere, and then from there on in, it's constant. It's just whatever it was right there, right? With a capital R in place for the little r the whole time. It does not continue its pattern going up this way. So it's constant, and then it falls away once you get outside of the sphere. Okay, so that's the point I wanted to make. Now let's look at an example with actual numbers. So, question: how much charge is on a conducting sphere of radius 0.15 meters if the potential of the sphere is 1200 volts? Okay, so here's our sphere. It's got a radius of 15 centimeters, and it is currently at 1200 volts. Like I said, the whole thing is at 1200 volts. And it must have this voltage because of some charge that is on it, some extra charge. It has been charged somehow. We know it's positive charge because we have a positive potential. But how much? Okay, so the actual V that's on and inside the sphere, right, that comes from that formula. Again, you replace the big R with a little r if you're moving outside, and then that V would go down. But 1200 is what it is actually, like literally on the metal, on and within the metal. That's the voltage of that sphere. Okay, so we want to know Q. We have the radius, we have the potential. So if I move things around, and let me just divide by the KE. There we go. There's a formula for Q. All right, so then we plug numbers in. There we go, and that ends up being 2.00 times 10 to the minus 8th coulombs. We could call that 20.0 nanocoulombs if we wanted to. So a little bit of charge, and that's what's causing the sphere of 15 centimeter radius to be 1200 volts. Okay, so that's the idea.